外一个是好。
要不等会儿回头再跟丽茹说一下，要什么？
没事没事。好 ，good good。
跟他说了一声，
不录了是吧？好好好好好。你要那个吗？你要讲一下吗？还是不讲了是吧 ？OK。OK， 我来快速的。OK OK。你要开场白吗？还是不需要是吧 ？OK 对。Okay. Today, this talk is for Antarfa Hacker House, and I'll be talking about the work recently published about the polynomial commitments. And first of all, I'll introduce what are polynomial commitments and why we should care about the polynomial commitments. So, yeah. Polynomial commitments. Okay. The first topic is what is why polynomial? Why polynomial? Okay, so the goal is that we want to build modern ZK proving system. Generally, we have two different types of arithmetization. In terms of saying that we want to convert that computation into some arithmetic objects. Then in order to we can prove using the cryptographic protocols to prove that the computation is correct. Okay. So the polynomial is powerful that we can encode a bunch of a very large set of commuting traces or circuits if we using the circuit to encode that computation that we want to prove. So polynomial kind of in short words, they can encode a very long a vector. So polynomial is for encoding vector. So in the past 2 week session, we talked about a lot about vectors. So how to prove the vectors and how to prove the relation between vectors. Even the vectors are hidden from the verifier. So polynomial will do more for us to encode that the vector is in different forms. For example, that we can encode that the vector A as the coefficients of some polynomial fx. Okay, let's write down the fx equals to a0 plus a1x plus a2x squared to the a dxd. The degree f equals the d. Okay. Now we can encode that. Okay. In the following, we can use different, many protocols for designated for polynomials to prove that okay, the vector has some properties, or if the vector represents a computing trace. Generally, we need more, more than, for example, 3 or to 30, up to 30 vectors. So to reason about the relationship between the vectors and relationship between the states. So if we see the vector as a transition, it's a vector of states with the state transition relationship between its two neighbors. Yeah, we can encode that vector as coefficient of x, and then we can also encode the vector as a evaluations of some fx, or use another symbol. We can encode A as the evaluation of gx, saying that we have different form of vector. So we can write the gx as this one, as a0 times lx plus a1 times l1x plus a minus 1 ln minus 1 x. Where the Lix is a Lagrange polynomial over a domain H. Generally, H is a multiplicative group over some field. Okay. Yeah. We can encode that vector as the coefficient of this form. Here, the Lx is a polynomial the Lagrange polynomial. So, for univariate polynomial, we can have this following definition of fx x like minus 1 for all the fx I minus 0 and yes, and then here domain H equals to omega 0, omega 1, omega n minus 1. Okay, just quickly brief the definition of Lagrange polynomial. That yeah, we can encode that vector into a polynomial like this, and also have the third representation, a third form of that of encoding a vector. So I can encode A as roots of some polynomial hx. So here we can write the hx is equal to x minus a0 times x minus a1. Okay. X minus n minus 1. If the length, there are n a in the vector, so which encoded form should we choose? It depends on that what property that we want to prove. So this is for the univariate polynomials. But for multivariate polynomials, there will be more encoding forms, right? And right. So what? So we encode the vectors into polynomial. Then how can it help us proving the properties of it? So it turns out polynomial quite useful just because they will have another very important theorem called I don't know how to pronounce. It's kind of a German Schwarzschild lemma. I think it's a theorem, but I don't know why it's called a lemma. It's a okay.
I mean, this is a.
So suppose, okay, here we use a univariate polynomial in either forms to encode a vector. So the verifier can easily verify if every element in the vector is correct with respect to some property. The basic idea here is that, okay, anybody knows that Schwarzschild lemma? Please raise your hand. So just quickly, sorry. Okay, all right. So in protocols, general prover will commit the prover will encode the vector into polynomials, and then send the polynomial to some trusted party, let's say Angel or something like that, and then the verifier will challenge if the polynomial is correct or not, or if the prover put a wrong number or maliciously modify some element in the vector. So the verifier will challenge the polynomial only once. Can check that if the prover is malicious, is dishonest or not. So the idea here is that, so if we encode a vector into polynomials in either of these forms, so we can draw a polynomial as a curve, right? Okay, it should be many curve, because if the order is 1 million, there will be kind of a lot of waves. Okay. Here's x, y, sorry, this fx, for example. And so what is domain H? Here is we choose some point the omega 0, omega 1, omega 2, blah, blah, blah. Okay. Right. Omega 3, omega 4, omega 5, omega 6, omega 7, omega 8, omega 9, 10. Suppose we have 11 point on the x-axis. Okay. Now suppose we use the second form to encode. So I should use the GH here. Then the A should be here, right? So the vector, all of them are on the curve, right? The A2, here the A3, A4, A5, A6, A7, A8, A9, A10, right? So if the prover is dishonest, prover probably will change this A2, for example. Okay, let's choose this one, A5. Put it here, right? It's A5 star. Let's put some, some value incorrect into the vector. And then the new gx prime should, its curve interpolate by this point, and then except the A5, instead of we put an A5 star into it. So the curve will be like right. Not easy to draw all of this, kind of. Yes, I should. Okay, the curve can be like this, kind of this. So I cannot, draw all of the. So the curve should across this point. Okay. I should use my computer. But anyway, you can understand, okay? So if only one point is not equal to the original one, the curve will change dramatically. The two curves only agree on the point like A0, A1, A2, A3, A4, A6, and all other places, like the points between omega 0 and omega 1, the two curves disagree with each other. So that means that we can easily pick a random x point like this, outside of H, to randomly pick it and check if two curves, the value, the intersection, the two intersections are equal or not. So the probability of successful checking, the probability of that the disagreement is kind of small d over big D. The big D is kind of huge. For example, we choose big D as a F. For example, like it's very large. Okay, it's very large domain. Then this probability could be very small, very, very tiny. So saying that the verifier only challenge one point can notice that, okay, the two curves are actually different. Okay. I think it's a fundamental idea behind the modern ZK systems, that the verifier, the cost of verification is relatively small and very small, and much smaller than the length of the vector. So it means that we can prove a very large, a very long combination trace by using just one challenge to make sure, okay, this combination trace is different from the correct correct one. Okay. Any question here?
Why does it need to be outside of H?
Because in H, almost all of 99% of points they agree with each other. For example, if this is not a prover, only change A5, so leave other AI unchanged. So the challenge, if the challenge point happen to be the omega I, so the results are equal with each other, right?
But if it's between also.
Yeah, if between omega 1 and omega 0, just outside of H, but it's still inside of capital D, then the verifier can find the difference, right? Can figure out the two curves are different. So, but if D is small and the capital D is quite large, that we don't have to worry about that because we the verifier happen to choose omega I kind of probability is quite small, right? Okay, this is the idea of a short-stable lemma, and I think almost every I'm not sure, quite sure, but most 99% of modern XNR system relies on short-stable lemma.
So
yeah.
The short-stable lemma also apply to the first and third.
Yeah. Yes, for sure. Yes.
Is that related to the TCP group systems?
I don't understand. Sorry. I don't understand the PCE. And yeah. Okay. Any problems here?
The degree of Gx there will be n minus 1.
Yes. Yeah. Here is n minus 1. N. Yeah. N. Yeah. Yes. Yeah. Then. So why commitments? So now, okay. The polynomial kind of very flexible for us to encode vectors. Then so why commitment? Okay. Let me share. Why commitment? So commitment is a cryptographic tool that we can, the prover and the verifier. The prover will put some alpha as a secret into or not secret, anything. Put alpha into a box and send the box to the verifier. The verifier cannot get alpha inside the box because the box has been locked. And then after rounds or some interactions or the prover will unlock this box to show the alpha, directly send alpha to verifier. Then verifier will check if the alpha prime if equals to the alpha inside this one. So by using that, the verifier will put also the alpha prime into a box to check if two boxes, if they are equal. To make sure that, okay, the alpha prime exactly the value inside the box. So we can see that, okay, the box kind of a one-way function. So once we put some value into box, and nobody knows that, okay, the value inside the box. But we can also put another value into box to compare the box. So, okay. And so the commitment is kind of useful for building protocols to improve that. Okay, for typical ZK or ZK proving system, the prover will put many stuff. For example, community trace. For example, alpha, beta, gamma, the vectors into boxes. And then the prover will prove the relationship between alpha, beta, gamma by using addition and multiplication and even more complicated properties. For example, inner product, or hard-mode product. Hard-mode products for has aka entry-wise product. For example, a circle, we use that symbol to to represent specify the hard-mode product. Kind of A0 times B0, A1 times B1, blah blah, to n-1 times B and then so on. So we can use polynomial complements to use complement to prove this, one. To prove vector, properties between vectors. And then, if we combine them together, we can build actually, turns out, very flexible protocols for us to prove this part very easily. Prove inner product and hard-mode products, and even, for example, grand product or circuit susceptibilities or community trace correctness or something like that. So then yes. Okay. Any question here? It's a very basic intuition behind the modern ZK snarks. So, okay, here I can. Yeah, maybe we shouldn't go deep. If we can successfully prove that inner product and the hard-mode product, we can easily prove a circuit or community traces. And it turns out if we can prove the polynomial, then we can easily prove the inner product and our hard-mode product. So then we combine them together, polynomial complement. So, okay, polynomial complement, that the prover has some fx as a secret. Sorry, put it here as a secret. Secret fx. And the proof to verify that this fx, so verifier will ask a alpha, and then prover want to prove that f alpha equals to some y. And then prover will send y to the verifier. So how can the verifier trust that, okay, the y is correct? So the prover will generate some pi as a general proof to prove that, okay, y is correct. So the verifier here will call the polycom.verify. The complement. So verifier will have the complement of the polynomial with the result y, with the alpha, with the pi. And the prover will generate the pi. It goes like this: polycom.proof f alpha and y, and send the pi to the verifier. So it's a picture of a polynomial complement. Okay, first of all, it's a complement. Additionally, that polynomial complement has to provide an interface that to prove an evaluation of polynomial. So here is the pi is the evaluation proof. Evaluation proof or argument. Okay. Well, pi is the evaluation proof. So what is the polynomial complement? Polynomial complement, first of all, it's a complement. It provides some interface or function that we can commit f into a put it into a black box using elliptic curves or Peterson comment or hash Merkle tree something. There are different approaches actually. This is an abstract picture of polynomial complement. First of all, the P committed the secret f into black box as polynomial complements give it into to the verifier, then verifier challenge a point just like this. Okay, here is the red point, here is a challenge point to ask the prover provide the result of y along with a proof to prove that okay, f alpha equals to y. Okay, it's quite a simple interface, quite a simple interface. It's very powerful. It's really powerful. So we can use this easily to build inner product and Hahnemann product and many proving system. So that's why I say that the polynomial complement is kind of the engine of modern Zk snarks. Because it looks simple and it looks like for example, if we change f into a program, then the picture becomes modern Zk snark, right? So we change f into a code, right? It's a code written in Rust, C, or a circuit. Yes, it's a minimum verifiable commutation. Okay. Okay, so any question here? Okay, almost half an hour. Okay.
So we provide y, and
yeah, provide y, yeah.
And we provide the proof that we've made that we've made the computation, or like how can I mention like pi as the.
Okay, it's an abstract notation here. Yeah. It depends on which polynomial complement we use. There's a lot of different schemes. Yeah. We will show later. It's abstract. So the interface of polynomial complements. There are a lot of polynomial complements. Okay. Everything's okay? Good? Okay, I'll remove all of those.
This is great. Can I take
Yeah.
someone took a picture?
I'm sorry.
No.
Okay. Okay. Yeah, I will remove all of this. To show you a brief history of polynomial complements, and there will be a lot of polynomial complements here. I do apologize that if I miss some important work, because I just read some of those. Okay. Okay, let me begin here. The brief history. Yeah. in the past 2 weeks, our ZK bootcamp sessions, we talk about a lot about protocols, Schnorr protocol and the inner product protocol. I will show the line of those work. Okay, here is I think the using Schnorr protocol to prove the circuit accessibility kind of from yes, CD 98, okay. 98, 90s. And then there's a lot of work. And we got the growth 09. You can Google that keywords. We can get the paper of it. Growth 09, kind of the minimal polynomial community I presented in my session was from this paper, kind of section 5. Okay, then, okay, the next milestone is BG12 to refine the approaches in growth 09. Here in BG12, that we can prove that two vectors into inside the two commitments, we can prove that okay, the shuffle relation. So the one vector is a shuffle of another. So in BG12. Then, okay, here we got, okay, we got BCC plus. There are kind of 5 or 6 authors here. I don't remember. The year 2016. This paper actually is the bulletproof, but not that bulletproof presented in the bulletproof paper. Actually, the main idea was presented in this paper, 2016. So same year with growth 16. In this paper, the idea of reduction and recursive reduction was proposed in BCC plus 16 paper. So we can use the Schnorr protocol or Sigma protocol to prove that a long vector, and instead of sending all the encrypted data to verifier, that prover can ask more challenges from a verifier, then recursively split and fold the response. And eventually we got the logarithmic size of proof and a logarithmic size of, linear size of verification time. And then we got the bulletproof paper. That paper is more popular than this one. But in bulletproof paper, it's okay, bulletproof. Bulletproof. I think the paper can prove that, yeah, 18 or, yeah, 18. It's bulletproof paper. So, yeah, this is a line of work that we presented in the past 2 weeks. Okay, here we will got another paper that probably a lot of people knows of, but it's called Hello. Hello as in Hello 2 proving system. Hello paper. The Hello paper kind of the idea is very smart that because in bulletproof, the verifier time is linear, it's ON, it's not succinct. So that means that we cannot put the verifier on chain. So using smart contracts, kind of a lot of gas cost, kind of impractical. But the Hello, the 3 authors from the ZKP team, they came up with a very smart idea that okay, even the verifier's work is ON linear time, but that kind of part of work can be batched or amortized if we simultaneously verify a bunch of proofs. And also, okay, the Hello papers propose that idea. Okay, we can build a recursive proof by using that idea. So I think from Hello paper we got another line of work: accumulation schemes, and folding schemes like Nova. Okay, folding schemes like Nova, a lot of Nova, different Nova, supernova, hypernova, something like that. Okay. Hello paper here, and the Hello paper is also depends on another paper called this one, the Sonic paper. I don't remember their authors. Sonic. Where's Sonic? Yeah, MBKM 19 is the paper has the name Sonic. And I think in the first, in the original Hello paper, they use Sonic as the front end of proving system. Now after Planck came out, then Hello changed it to the Planckish front end. Then why we got Hello 2, so number 2. The Hello 2 is Planck plus bulletproof IPA as the backend polynomial commute. Yeah, and the PSE changed the polynomial commutes to KZ10, then we got another version of Hello 2. Okay. Here's Sonic. And the predecessor of Sonic is another work. Okay, let me check. Yeah, GKMMM 18. Sorry. GKMM. Yeah, 3M. 18. So the paper, the first G is growth, young growth. I'm not sure I pronounce his name correctly. Growth. And the idea is that propose this so-called updatable SRS. Updatable SRS. Saying that, okay, we can put CRS like tau square, blah, blah, aka powers of tau. Power of tau. Okay, the idea here. But actually, the power of tau idea kind of, compared to growth 16, that we have to do a trust setup for each circuit. But for updatable SRS, we only get a common, say power of tau as SRS. That makes okay. The SRS can be reused again and again for a different circuit. Okay. Yeah, I think its work is based on KZ10 for sure. But the interesting is here is that the predecessor work is not based on KZ10. It's based on another paper, growth 10. Also 2010, the same year with KZG10. I put the KZG10 here. Sorry. Put it should be here. KZG10, the most popular polynomial commutes right now. So if Google KZ10 got a lot of articles to describe how it works. Like KZ10, growth 10, the same year. And also, they are published in the same conference. Sorry?
It's Asian crypto.
Yeah, Asian crypto, in crypto 2010. Actually, they are kind of seemingly solving the same problem, but I think they didn't realize that until many years ago, after. So, grows 16, and then there's another work, GGPR 13, and that's also produces the work of Pavel Tall, because GGPR 13 and Pinocchio, another paper, Pinocchio published the same year, and the Gross 16 is based on trusted setup that for per circuit trusted setup. And okay, so how about the KZ10? And some people noticed that, okay, this work kind of useful. Then they build another work based on KZ10. We call it PST13. PS13. It's a KZ10 over multivariate polynomials. Multivariate. Okay, I think this work is also the base of Sonic. Okay. There'll be many lines. Okay, many lines. I do apologize. Okay, there could be another line. There's a lot, so let's go this way. Okay. After PST 13, probably go here. We got another very important paper, I think, like a V-circle. It's a work for proving a database that the correctness of query of some database. V-circle. Let me find his ZKP 17. Sorry. ZGKPP. Okay. I think in this paper, the authors proposed the modern concept of polynomial increments, but they gave that scheme another name called the VPD, verified polynomial delegation. So verified polynomial delegation, VPD. Okay, put it here, VPD. Okay, kind of a renaissance of a polynomial increment here, right here. And simultaneously, the people in the Sonic paper, because they reused the work from Gross 10 and PST 13, okay, those authors realized that, okay, probably there's something called a polynomial. Polynomial, if we build something like only prove the property of polynomial, then the proving system will be easier to construct. I think from Sonic and it was from V-circle, but V-circle kind of 1 year before, almost 1 year before Sonic. So from V-circle, there's a lot of work to improve that polynomial increments. So I think the next work is XZZPS, XZZPS 18. Yeah, the paper published 2019. It's called Libra. If anybody quite interested in GKR, I highly recommend this paper to you. The paper is well written, and a lot of algorithms present in the paper that I highly recommend the paper. You are interested in GKR system. So the Libra improved the polynomial increments by using, because the V circle, I think, kind of using bulletproof. I don't remember that. Based on, yes, I think I should draw a line here. And also another work came out. Yeah, I don't remember the authors. I'm sorry. The system is called Herax. If you read the paper of Nova, right, the Microsoft Nova, this do use Herax as a Herax PC as the polynomial commitments as the backend. The V-circle, so the Herax based on V-circle and then improve the polynomial commitments and turns the polynomial into zero knowledge to achieve zero knowledge polynomial commitment. And then I think after Libra we got Virgo kind of there are 4 authors here. ZXZS. I think 19 or 20. It's a polynomial commitment. Okay. Circle is based on IPA, and the Libra based on KZG10. Okay, based on this one. So it means that we have to do trust setup, but for it's not a trust setup per circuit, kind of a general universal trust setup. And from Virgo will use the F-Fry, aka stack stuff into this GKR system to make Virgo. So we'll draw another line of Fry paper BBHR 18, the Fry. And then the Fry goes further like this, and the BGKS, BGKS, right? Am I right? They call it deep Fry. Using deep method to improve deep Fry to improve the Hamming distance, in order to reduce the proof size. BGKS 19, and then BCSI 20. It's a breakthrough. Heavy math warning. But this paper proves a very important proximity gaps. Seeing that, okay, for Fry we can safely reduce the current number of the queries in order to reduce the proof size. Just because they found a smarter way to prove that, okay, that approach will be safe. Please trust them. Yeah, BCSI 20. Okay. BCIKS. I'm sorry. 5 authors. So I'll quickly go into the modern one. The proving system proposed recently about all about the polynomial commitments. From proximity gap, we will have the following work from ECFFT, BCKL 22. Okay. BCKL 22, ECFFT. And then circle stack. I think a lot of many of you want to read the paper, circle stack. What's the name of the authors? HLP 24. HLP 24. But this work is also depends on another work, HLN 23. So in HLN 23, they actually found that, okay, we can build a group to build a faster FFT over a circle. And then, okay, I think February this year, they proposed circle stack. Okay. And to try that. There's also a paper published last week called RC stack from Yinggang Yang. And if you're interested, please check it out. It's from here and based on here, probably. Yes. Yeah, let's go this way. Okay, after the Virgo is GKR plus Fry, and then the same group, they come up with another popular, Orion. Authors kind of XZS22, 22. And there will be another predecessor work from Jiaxing Sailor's group. It's called GLSTW21. It has a name like a breakdown.
It was published in the 2023 group.
Yeah, but the paper was written in 21, before Orion. Because Orion is kind of an organization using different encoding algorithm to make the prover strictly linear. Yes. And before breakdown, we have kind of a lot of work. Oh, sorry, I got no space to write them all. There's another one I should mention, that AVH19 Lahiro work. I think Lahiro work is producer of this one. The first paper to propose that proximity gap, the most important concept for understanding understanding Fry. So proximity gap. So maybe you can check out this. I think they have another journal version published 23. It's a long version of the paper that kind of readable, understand the basic idea of Lahiro, and then there's some work inside. Some I should mention is BCG20, and a lot of but do apologize, no space to write them down. And from the breakdown, we got another very exciting lines work from irreducible team. This first work is called DP23. DP23, and to prove the breakdown of polynomial equivalent, and then they come up with DP24. It's got a name, Benius, right? How to pronounce it? Benius or Benius? Yeah. Okay, it's a polynomial equivalence over Banach field. F2. Yeah, it's a Banach field, polynomial equivalence. Yeah, very exciting work, very exciting. And now this year they published another work called the Frobenius, right? Frobenius to build a fry about this fry. Where's fry? Okay, here. Yeah, yes. And yeah, there's many things have published recently. Let me draw them down. Yeah, if you are interested, you can pick some of those to try. So I think recent work kind of very exciting. Let me put it here. Base fold. Yeah. So what's the author's name? Yeah, ZCF23. ZCF23. The base fold work based on Fry and another work, kind of yeah. Germany, yeah, BH. Germany, where's Germany? BCHO, sorry, BCHO 21 or 22? BCH. Yeah, Germany. It's a proving system, polynomial communes, which can be memory efficient. So we can build for example, we can put proving system into web browsers to only require a small amount of memory footprint. So this proving system is also called elastic proving system, saying that if we have enough memory, then we can drive as far as we can. And if the memory is limited, then we can slow down, but using a smaller memory footprint. So Germany. And then after base fold, we got the paper published just last week. Yeah, it's called ACFY 24, and it's called 24.
This year.
Yeah, it's I don't how to pronounce this. Something like that. And this paper combined another work, stir. Maybe some of you already implement this algorithm, stir. Let me stir. Yeah, ACFY 24, same author. ACFY 24.
Stir is based on fry.
Yeah, stir based on fry. Fry and deep fry. And yes. And sorry. And then there's another paper published last week based on base fold called deep fold. The authors GLHQTZ. Wow. GLHQTZ 24. Okay, all of these are new polynomial communes. You can see a lot of them. So Not finished. Be patient. And okay, along this line, still lines work. Gemini, the predecessor work kind of a BCG 20, I think. I'm not sure. Okay, Gemini. And after Gemini, we got the zero morph from Aztec team morph. KT23, I think. Yeah, KT23. It's Gemini and zero morph. They are two very special polynomial commutes. They kind of as adapters to reduce multivariate multilinear polynomials into univariate polynomials. Seeing that we can combine zero morph with KZ10 or any univariate polynomial commute to, then we have a MLE polynomial commutes. And the MLE polynomial commutes are very useful combined with sum check or GKR. Okay. And yeah, there's others. GKR. There's someone based on here. We have Dory. I think which year? 21 or 22? Oh, sorry, 20. Yeah. There's supposed to be more lines between them. Yeah. And before FRI had kind of IOP and PCP along a very long lines forward. And so yes. And after Sonic we got two system like Planck, GWC 19, and then Marlin. Yes. Okay, no space for Cruise City. I'm sorry. It's not a polynomial commune-based Promethean system. Yeah, there's a lot. Okay, this is a picture of showing that in the past 10 years and how fast the progress, amazing progress made by the people. Yes. Yeah, probably I missed many important work because I just read part of this work. Kind of. Yes, I think. Okay. Thank you very much for coming. Yeah.
What's the relationship?
Sorry?
What's the relationship between baseball and Germany?
Baseball, yeah, yes, okay.
My institution is that maybe baseball they use the multilinear polynomial, and therefore the multilinear polynomial use the Germany the folding polynomial way from the Germany.
Yes. And Germany use KZG. So yeah, KZG. It should be KZG here. And Germany combined GKG and VFI. So it sounds weird, right? Because they are same they are both polynomial commutes, but the Gemini combined KZG10 and FRI to build a MLE polynomial commute. So okay, the Gemini just used the basic idea of FRI and over KZG10 and provide a MLE polynomial commute. I'm sorry, the basefold using the idea of sum check with a Frey, and the idea from the Frey in Gemini form, and combine them together to get a MLE polynomial equivalence without helping with the adapters. Yeah.
So where's the place for hyperplug?
Oh yeah, yes. I'm sorry. Yeah, hyperplug. The hyperplug should be here. Yeah, hyperplug. Yeah, hyperplug. So hyperplug, I think in the paper they proposed 3 different MLE polynomial equivalents. One using Libra, and another one using Gemini, and another from Orion. I think so. Yes, hyperplug here. It's sum check based Planck. The Planckish at the front end, and then using sum check to reduce the polynomials into just one MLE polynomial, and then invoke a MLE polynomial equivalence to finish the whole proving process.
So consider the hyper-KDG part of Gemini?
Yes, I'm sorry for that. Hyper-KDG, yeah, hyper-KDG kind of Gemini. So I'll put it here. Hyper-KDG. I think no paper published. Yeah, by SETI. 20, yeah, last year. Hyper-KZG, I think, and the KZ10. Yeah, KZ10. Oh, yes. Hyper-KZG. Yes. Thank you. Yeah, space is kind of exciting, and every week there'll be more on the way. There's some from poly prime, from BUA. I haven't read the paper, so I'm not sure the dependency between them. Yeah, okay. Yeah, polyframe. Yes. Kind of, yeah, polyframe. Yeah, there's another new one that I haven't read. Yeah, I'm sorry. Blaze, published last week or yeah, at least this month. Blaze, from Alexandra's Chiaza's group. Blaze, but I'm not sure. I'm still. I know nothing about that. Only the name. Okay, any question?
What do you think is a lot of more research required in what area where you think there should be more exploration in regards to if we see this network of papers, is there a certain area where you think there should be more research done?
No, I don't know. I don't know. Yes. And some of those are readable, and some of those are very hard. Yeah.
So the default is also based on the diffrag, right?
Yes. 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 Correct. Yes. Deep fry. Yes. And I think they kind of like a tree, you know. They're supposed to be more branches. DAG. Yeah, I think the talk is over. I think. Why so quiet?
Very involved.
Unimpressed.